So in this 13th podcast, we're going to focus on the mole and how it links to balancing chemical equations. In the previous podcast, we've seen how to balance the chemical equations, and it tells us how many atoms or molecules of reactants we need to get our products. So let's take a look at the reaction we saw in class the other day. We put sodium metal into water, and we got sodium hydroxide, which was dissolved in the water, and hydrogen gas. So the reaction looks something like this. This is not balanced. If I throw a few 2's in there, the equation becomes balanced. And we can see that we need 2 atoms of sodium, 2 molecules of hydrogen, which gives us 2 units, let's say, of sodium hydroxide and 1 molecule of hydrogen gas. Now when we did this in class, we had an excess of water. We had loads of water left over, if you like. We put in a tiny bit of sodium into loads of water, and we got a small amount of sodium hydroxide. Now chemical engineers who want to manufacture products from reactants will actually want to add just exactly the right amount of the reactants. They won't want to waste any. Now obviously we can't count out 2 atoms of sodium or 2 molecules of water. They're just simply too small. The mole allows us to link the number of atoms or molecules in a substance, something we can't count, and the mass of the substance in grams, which we can measure easily. Let's look at the atomic mass, or the average atomic mass. Now this is something which is listed for all elements on the periodic table, and here's carbon from the periodic table. We can see carbon, symbol C, element number 6 or 6 protons, has an average atomic mass of 12.01. The concept of the mole links this number to the actual measured mass. Now for example, if we measure out 12.01 grams of carbon, we know that we've got 1 mole of carbon atoms. Now the mole is just a number. Let's take another one. Sodium element 11 with an average atomic mass of 22.99. If we measure out 22.99 grams of sodium, we've got 1 mole of sodium atoms. Exactly the same number of atoms as if we measure out 12.01 grams of carbon. Different masses, but same number of. Now this works for molecules as well. We have average molecular mass. Now here's oxygen. Oxygen element 8, average atomic mass 16.00. Hydrogen element 1, average atomic mass 1.01. So let's look at oxygen gas. Oxygen gas is O2, 2 atoms, so that's 16 times 2. So the molecular mass, the average molecular mass of oxygen is 32.00 grams. Let's have a look at water. Water is H2O, that's 2 hydrogens and 1 oxygen. Do the math, 2 times 1.01 plus 1 times 16 gives us 18.02, so the average molecular mass is 18.02, so the mass of 1 mole of water is 18.02, exactly the same number. This time we write grams. So if I have 18.02 grams of water, I know I have exactly 1 mole of water molecules. So how many particles, atoms, molecules, whatever, are there in a mole? Quite a lot. 6.0221417930 times 10 to the power of 23. That's a very large number. That number. Or we could say 602,000 billion. That's a lot more than even grains of sand on a beach. So it's very, very big. But we don't really care about the number. The important thing is a mole of carbon, or a mole of hydrogen gas, or a mole of water, or a mole of anything has this number in it. So let's go back to the sodium-water reaction now. So this is the equation we had. Now for a complete reaction with no excess reactants, no waste, we must react together 2 atoms of sodium, 2 molecules of water. Or any ratio of that. It could be 4 atoms of sodium and 4 molecules of water. it'll just double everything through. Like in a math equation, we can double everything, do the same function to all parts of the equation, and the equation still balances. So it could be 8 atoms of sodium, 8 molecules of water, giving us 8 units of sodium hydroxide and 4 of hydrogen gas. Or 2 moles of sodium. That's obviously a very big number of atoms, but 2 moles of sodium atoms, 2 moles of water gives us 2 moles of sodium hydroxide and 1 mole of hydrogen. Or even 1 mole of sodium, 1 mole of water gives us 1 mole of sodium hydroxide and half a mole of hydrogen. Now let's link these moles into the measurable quantity, which is mass in grams. So we said that we can react 2 moles of sodium with 2 moles of water, and we'll get 2 moles of sodium hydroxide and 1 mole of hydrogen gas. So we have the molar mass here of sodium, 22.99. 2 times that number gives us 45.98 grams. We have the molar mass here of water, 18.02. 2 times that gives us the mass of 2 moles, 36.04 grams. This is sodium hydroxide. Now, sodium hydroxide, NaOH, 2 moles of that. Now, sodium, the average atomic mass, 22.99, plus oxygen, 16.00, plus hydrogen, 1.01. Add those together, we get exactly 40 grams. 1 mole of hydrogen gas, hydrogen, H2, average atomic mass of hydrogen, 1.01. Multiply that by 2, and we get 2.02. Now, going back to sodium hydroxide, this is only the mass of 1 mole, so the mass of 2 moles, we need to multiply that by 2, which gives us 80 grams. So we're expecting 80 grams of sodium hydroxide and 2 grams, just over 2 grams of hydrogen out of this reaction. Now these numbers, of course, should add up to the mass of the reactants. Conservation of mass we've already discussed, 45.98 plus 36.04. Add them together and we get 82.02. The total mass of the reactants. Total mass of the products is going to be the same. You can see that very quickly. 80 plus 2.02 is 82.02 grams. Now in a reaction, it's very unlikely you're going to have a whole mole or 2 moles of substance to react. In class, with the sodium and water example, we were using a small amount of sodium, maybe about 0.3 grams. Now what fraction of a mole is this? We need to be able to work out how many moles we've got so we can decide how many moles of water we would need. So that's quite straightforward. We want to know how much of a mole 0.3 grams of sodium is. So this is the calculation we would do. 0.3 grams, that's how much we've got. Divide that by the average molar mass, or the molar mass, which was 22.99 grams. Divide those two together and you will find the fraction of a mole that you have. So 0.3 divided by 22.99 gives us 0.013 of a mole. Let's write that down. 0.013, and the symbol we use, or the shorthand we use, is just mole. So 0.013 mole of sodium in our reaction. So how much water would I need for a complete reaction? Well, if we think back to the equation, let's just flick back. We can see that we need 2 moles of sodium and we need 2 moles of water. So we need the same number of moles of water as we do sodium, the same number of moles. So how much water would I need for a complete reaction? 0.013 mole of water. But how much water is that? All I need to do is multiply this number by the molar mass of water, and I have my answer. So I'm going to multiply that by 18.02, which is the mass of 1 mole of water. So we have 0.013 moles multiplied by 18.02, the molar mass of water, and I get 0.23, let's round it to 2 significant digits, 0.23 grams of water. So let's write that down. 0.23 grams of water. So in our little demonstration experiment in class, if we really did have 0.3 grams of sodium, we'll have only needed 1/4 of a gram of water, or that's 1/4 of a milliliter of water to complete the reaction, a very, very small amount of water. So clearly we had way too much water. Now, here's something to try for yourselves, and I want you to write this down, write your answers down, bring them to class. Now, potassium reacts with water, as we saw as well. The reaction 2K, K is potassium, plus 2H2O gives us 2KOH plus H2. So the reaction is almost identical, except for we've substituted in potassium. Now, if I had 10 grams of potassium, what I want you to work out is how many moles of potassium that is, and also how many moles of water do I need for a complete reaction, how many grams of water is that, and also how many moles and how many grams of potassium hydroxide will I have after my reaction is complete. So write these answers down, show your calculations, and bring them along to next class.